So we're going to be going over Project 4C, the simple pendulum. The problem statement begins with, in section 4.8, we discussed the simple pendulum consisting of a mass m suspended by a rod of length L having negligible mass, and derived the nonlinear initial value problem d squared of theta over dt squared plus g over L times sine of theta is equal to 0, given the initial conditions are theta of 0 is equal to alpha and theta prime of 0 is equal to 0, where g is the acceleration due to gravity and theta of t is the angle the bottom makes with the vertical at time t. Here it is assumed that the mass is released with 0 velocity at an initial angle of alpha, where alpha is between 0 and pi. We would like to determine the equation of motion for the pendulum and its period of oscillation. Here's the accompanying figure, and we move into part A, which says, use equation 1 and the energy integral lemma discussed in section 4.8 to show that d of theta over dt squared is equal to tg over L, all times cosine of theta minus cosine of alpha, and hence dt is equal to negative square root of L over 2g times 1 over the square root of cosine of theta minus cosine of alpha d theta. So the solution here, in order to make what we have in equation 1 up here look like we're trying to make it in equation 2, what we first start off by doing is multiplying the entire equation by d theta over dt. What this allows is for us to turn it into this form, where we have d over dt, and then in brackets 1/2 d theta over dt squared minus g over L times cosine of theta is equal to 0. And we can easily confirm that this right here, equation 5, is equivalent to equation 4 here. If you just take the derivative of equation 5, and you'll see that you get equation 4. So once you do that, you're going to be able to take the integral of equation 5, which we have down here, the integral, and you take the integral with respect to this side, you're going to be left with the 1/2 over d theta over dt squared minus g over L times cosine of theta. And on the right-hand side, when you integrate 0, you're just going to be left with a constant because the derivative of any constant is just 0. And pulling out 1/2 from the left side of the equation, and then you multiply to the right side of the equation, you'll still get a constant. So this goes away, and all we're left with is this portion here. We can solve for the constant by using the initial condition, theta prime of 0 is equal to 0, and theta of 0 is equal to alpha. We solve, and we plug in, and we solve for the constant, and we end up getting that the constant is equal to negative 2g over L times cosine of alpha. Once you plug this constant back into equation 8 over here, you're going to get that the d theta over dt squared is equal to 2g over L times cosine of theta minus cosine of alpha. This equation 12 here matches what we were trying to prove back in equation 2. Now, we also want to prove equation 3. So in order to do that, we need to take the square root of both sides of what we just found of equation 12. So we take the square root, and here you can see the d theta over dt squared was on the left side, but now I just moved it on the right side just to make all these, equally spaced. So now we just flipped it over here, and we're taking the square root. We have plus or minus square root of 2g over L times cosine of theta minus cosine of alpha is equal to just simply now d theta over dt. And in order to solve for dt by itself, you're going to have to multiply by dt on both sides of the equation. And you go through with the algebra, and we end up finding that dt is equal to negative square root of L over 2g times 1 over square root of cosine theta minus cosine of alpha, all times d theta. And this equation here looks exactly like what we were supposed to get in equation 3 up here. Moving on to part B, use the trigonometric identity cosine of x is equal to 1 minus 2 sine squared of x over 2 to express dt by this equation. Dt equals negative 1/2 square root of L over G times 1 over the square root sine squared of alpha over 2 minus sine squared of theta over 2 d theta. So all you have to do is take equation 3 that we found in the very beginning and replace them, the cosines with cosine, replace the cosine theta and the cosine alphas with the respective trigonometric identities that we have right here. So you will just place theta for x, and then you'll place alpha for x, and you should get the equation down here. dt is equal to negative 1/2 times square root of L over G times 1 over square root sine squared of alpha over 2 minus sine squared of theta over 2 d theta. In part C, make the change of variables where you now have sine of theta over 2 is equal to sine of alpha over 2 times sine of phi, and show that the elapsed time t for the pendulum to fall from the angle theta is equal to alpha, and this corresponds to a phi value of pi over 2, to the angle theta, which is equal to beta, and this corresponds to a phi value of, I guess, big phi, when alpha is greater than or equal to beta, which is greater than or equal to 0, given by this series of equations here. And we're going to let k equal sine of alpha over 2. So we need to start making the appropriate substitutions where sine of theta over 2 is equal to sine of alpha over 2 times sine of phi. And we're going to do that by plugging it into this part of equation 22, this middle portion. So we're going to basically take sine of alpha over 2 times sine of phi and plug it into this part of the equation right here, the sine squared theta over 2. And you're just going to square both sides here. And you're going to get something that looks like this, what we found in equation 23. Notice that when we make the substitution, we're going to have to change the limits of integration. So the limits of integration at first were from theta equals alpha to beta, but in the problem statement, it gives us the corresponding phi values of pi over 2 to big phi. Not only are we going to have to make those substitutions, but we're going to have to make the substitutions of d theta. And in order to do this, we are going to use the given sine of theta over 2 is equal to sine of alpha over 2 times sine of phi. And we're going to take the derivative with respect to theta and phi. Once we do that, we're going to find out that d theta is equal to 2 sine of alpha over 2 times cosine of phi all over cosine of theta over 2 d phi. Now, we're trying to solve for just to be in terms of phi, and here in the denominator we have a theta. We need to get rid of this theta, so we can easily do that by the identity here. So cosine of theta over 2, that's just the square root of cosine squared of theta over 2, because the square root and the square will cancel out. And then we can use the trigonometric identity, cosine squared plus sine squared is equal to 1. So we're going to put inside the square root 1 minus sine squared of theta over 2, which is also equal to square root of 1 minus sine squared of alpha over 2 times sine squared of phi, given the identity we have in the problem statement up here. Now, we're going to let k equal sine of alpha over 2, and then we should get something that looks like this. Once we have this equation where we can plug in square root of 1 minus k squared sine squared of phi, we can plug that in for the cosine of theta over 2 that we needed to get rid of here in the denominator. We now have our equation for d theta, and we can replace this in the equation here. This d theta we are now going to replace with all this down here. And now our integral will be with respect to d phi. This is what it's all going to look like. It's kind of messy. So this is just a series of algebraic operations that we can do to simplify. So we're going to replace everything that we see where we see a sign of alpha over 2. We're going to replace that with a k. And it kind of helps clean things up. So by the end of the simplification, we're going to get the desired equation, negative square root of L over G from phi is equal to pi over 2 to phi equal to big phi, capital Phi. And that matches what we need it to in equation 22. So it matches this one up here. Now for part D. The period of the pendulum is defined to be the time required for it to swing from one extreme to the other and back. That is from alpha to negative alpha and back to alpha. Show that the period is given by p equals 4 times the square root of L over G, the integral from 0 to pi over 2 times 1 over the square root of 1 minus k squared sine squared of phi d phi. The integral in 38 is called an elliptic integral of the first kind and is denoted by f of k comma pi over 2. As you might expect, the period of the simple pendulum depends on the length L of the rod and the initial displacement alpha. In fact, a check of an elliptic integral table will show that the period nearly doubles as the initial displacement increases from pi greater than 8 to 15 pi greater than 16 for a fixed length. What happens as alpha approaches pi? The period of the pendulum denoted by p is equal to the integral t that we derived in equation 37, right here, from alpha to negative alpha and then from negative alpha back to alpha. But from the problem statement from part C, way up here, where they gave us the change of variables, we know that negative alpha, a negative alpha value is going to correspond to, well, no, alpha to negative alpha, and then from negative alpha back to alpha, it's basically from pi over 2 to negative pi over 2, and then from negative pi over 2 back to pi over 2. The period is the magnitude of 37, this one right here. So we can disregard this negative sign. We're going to be left with the period p is equal to square root of L over G, the integral from pi over 2 to negative pi over 2. And we're going to have the same integral over here, square root of L over G, this time from negative pi over 2 to pi over 2. Now you can see that it's symmetrical. So we can rewrite the equation as 2 times square root of L over G from 0 to pi over 2. Same thing over here. It's going to be symmetrical. So we can do 2 times the integral 0 to pi over 2. And we're going to be left ultimately with 4 times square root of L over G, all times the integral 0 to pi over 2, 1 over square root of 1 minus k squared sine squared of phi d phi. And it matches 41 as it was supposed to. Or it matches 38 as it was supposed to. Part E. So we're going to use equation 38 to show that negative t plus p over 4 is equal to the square root of L over G times the function k comma phi, where f parentheses k comma phi is equal to this integral here. So for a fixed k, f of k comma phi has an inverse denoted by Sn ku that satisfies u is equal to f of k comma phi if and only if Sn of k comma u is equal to sine of phi. The function Sn k over u is called a Jacobi elliptic function and has many properties that resemble those of the sine function. Using the Jacobi elliptic function Sn ku, express the equation of motion for the pendulum in the form shown here below. Now, to start, we're going to go back to equation 38, which was this period equation. And we're just simply going to divide by 4 on both sides, leaving us with this. And we know the equation for t from equation 37. It was this one right here. And if you subtract t from both sides of this equation, you'll be left with a negative t plus p over 4. And then this was the integral for p over 4. And this is the integral for negative t. You combine it all together. You can see here that the inside of the integral is the same. And you have the limits of integration from 0 to pi over 2, and then from pi over 2 to big phi. So you can combine it into one single integral where you have negative t plus p over 4 is equal to the square root of L over g from 0 to big phi with 1 over square root of 1 minus k squared sine squared of phi d phi. Now we're going to let f of k comma phi, it's going to be equal to the integral portion. So you can substitute that in, and this is the equation we're left with. And this verifies equation 42. To derive equation 43, we will start with the fact that for a fixed k, f of k comma phi has an inverse denoted by Sn k comma u, and this satisfies u is equal to f of k comma phi if and only if Sn of k comma u is equal to sine of phi. If the inverse is denoted by Sn of k comma u, where u is equal to f k comma phi, then the inverse is Sn k comma f of k of phi, and we need to solve for f k comma phi by rearranging 42. This is pretty easy because all you have to do is just move this right here, the square root, onto the other side. It leaves you this portion right here. And then you can just plug in to the Sn k comma f of k comma phi. So the k value that we have is just k. The f of k of phi is going to be this right here, and you're going to plug it into the equation. So to relate what we have so far, we know that sine of phi is equal to Sn of k comma u. This is given from our problem statement. And we just also plugged in u is equal to f of k comma phi, also given from the problem statement. And then what we just found, we're going to plug that in right here. So ultimately, we have sine of phi equal to all this. So to make it look like the desired equation, we're going to multiply k on both sides here. We're going to be left with a k sine of phi and k times all of this. So we're pretty close. All we need to do now is make the left side look a little bit more like the desired equation. And we recognize that in part C, we let k equal to sine of alpha over 2. Now we're going to substitute the k into the left side of the equation. It gives us this identity that we were dealing with earlier, sine of alpha over 2 times sine of phi. And it's going to be equal to the right side. The right side is unchanged. Using the identity from part C, we know that sine of alpha over 2, or the sine of theta over 2 is equal to sine of alpha over 2 times sine of phi. We're going to substitute that in here on the left side. And we're just going to take the inverse sine on both sides. And then we're going to multiply by 2. And this leaves us with the equation that we were trying to get in the very beginning for values of 0 less than or equal to t less than or equal to p over 4. Now, finally, part F was a little tricky. So we're given that the length is equal to 1 meter, gravity is 9.8 meters per second, and alpha is equal to pi over 4 radians. We're going to use either Runge-Kutta algorithms or tabulated values of the Jacobi elliptic function to determine the period of the pendulum. So we remember that k is equal to sine of alpha over 2, and we know that k is equal to sine of pi over 4 as we were given here. plug that in, divided by 2, so sine of pi over 8, and it gives us this decimal value. From the problem statement in part C, we remember that when the angle theta is equal to alpha, it corresponded to a angle of phi, which is equal to pi over 2. Therefore, we have f of k comma phi is equal to f of this decimal 0.32683.4324 comma pi over 2. Now, we're supposed to use the tabulated values of the Jacobi elliptic function to be able to find the period of the pendulum, although that was a bit tricky. So just estimating the period using the standard formula, t equals 2 pi over square root of L over G, we're going to plug in the values that we have, and we get that the period is approximately 2.01 seconds. All right, well, thank you. That was problem for project 4C. Thank you.